So in the last lecture, we were discussing some concepts of electric field and potential, which were not there in NCERT. So we discussed potential and field due to a ring. After ring, we'll do some numericals, but first let's discuss some theory. The next is electric field due to solid sphere. We'll do field and potential both due to a solid sphere. Now, do you remember, anyone remember the expression of electric field due to a hollow sphere? Like if we have a hollow sphere, this is a hollow sphere, and I ask you to calculate field at a distance r. What is the expression of field at a distance r from a hollow sphere? Rishma? Field at a distance r from a hollow sphere. What is the expression of field, Rishma? Yashika, what is the expression of field at a distance r from a hollow sphere if that sphere has some charge q? This we did when we were doing Gauss law. For field due to a hollow sphere was kq by r square. Is there anyone in class? Anshika, Arpit, Hishma, Mehraj?
Yes,
Okay, people are in class. So this is field due to a hollow sphere. At a distance r, the expression of field is kq by r square. But instead of a hollow sphere, if I give you a solid sphere and I ask you to calculate electric field due to this solid sphere. So this is a solid sphere and solid is non-conducting. Solid non-conducting sphere. So this solid sphere have some charge on its surface, and charge is also distributed inside the sphere. So the type of charge density that we'll be using for this solid sphere will be rho. So it will have charge density, volume charge density of rho. You're supposed to calculate electric field due to this sphere at a distance r. I take this point A, which is outside the sphere. Then I will take a point on the surface of the sphere. Then I will take a point which is inside the sphere. So these are the points at which we will calculate electric field due to a solid sphere. So outside the sphere, the charge over the sphere is q. If you want to calculate field outside the sphere, then outside expression is same as that of a point charge. Outside the sphere, the expression of field is just like a point charge, kq by r square. If you want to calculate field on the surface of sphere, it's kq by capital R square. This is electric field on the surface. If you want to calculate electric field inside the sphere, so this is the point inside the sphere. This point is at a separation r from the center of the sphere. Then inside the sphere, field is rho r by 3 epsilon. Where r is the separation of the point inside the sphere from the center. Can you convert this in terms of q, charge, Arpit? Do you remember any relation between charge and volume of the sphere and volume charge density? Noah, what's the formula for volume charge density? Yashika?
Sir, total charge by total volume.
Total charge by total volume. So total charge is q. Total volume of the sphere is, the radius of the sphere is capital R. So total volume of the sphere is 4 by 3 pi r cube. So it's rho by 4 by 3 pi r cube. So instead of this rho, you can substitute this whole term. When you do the substitution, then electric field inside the sphere is it's q by 4 by 3 pi r cube into small r by 3 epsilon. So 3 will cancel this 3 and you will get that electric field inside the sphere is it's qr by 4 pi epsilon naught r square. This is electric field inside. Sorry, not r square, but r cube. The next task is to plot electric field versus position graph, E versus R graph. So this is R and this is E. When you plot this graph, let's say this is R equal to 0. This is the point at the center of the sphere. This is R equal to capital R. This is the point on the surface of the sphere. This is R is less than capital R. This is the point inside the sphere. And then R is greater than capital R. This is the point which is outside the sphere. So when you plot this graph, say this is electric field inside. If you calculate at center, then at center the value of R is 0. When you put R equal to 0, you will get that electric field at the center is 0. This is the value of field at the center is 0. So at center it's 0. Inside field is directly proportional to R. So the shape of the graph will be a straight line. Inside it will be a straight line graph. When you go outside, then your field is inversely proportional to R square. When you go outside, it's inversely proportional to R square. It goes like this. So E inside is directly proportional to R. E outside is inversely proportional to R square. That's why this shape, this hyperbolic shape. So this is electric field due to a solid non-conducting sphere. Along with solid non-conducting sphere, sometimes it asks you to calculate electric field inside a cavity. Like this is a solid sphere. This is a solid sphere which is non-conducting. Yeah. This is the solid non-conducting sphere. The radius of the sphere is capital R. You're supposed to calculate electric field inside the cavity. This is the cavity. This is the cavity. Cavity means from this solid sphere, you remove some portion. You remove some portion, a portion of radius, some small r. The separation between the center of cavity and the center of the sphere is A. The whole sphere is charged except cavity. Cavity means this portion is being removed. You have removed this portion. You cut this portion from the sphere. So there is no charge inside the cavity. And the separation between the center of the sphere and this center of cavity, this separation is A. So when you calculate electric field inside cavity, electric field inside cavity, it comes out to be rho A divided by 3 epsilon naught. So this is the expression of field inside the cavity. See, inside the cavity, field depends upon A. And what is A? It's the separation between the center of the cavity and the center of the sphere. If I take point anywhere inside the sphere, anywhere, this A will not change, which means if I calculate field at any point inside the cavity, the expression of field remains same. So you can say that this field is inside the cavity, field is uniform. It's uniform inside the cavity. Means whether you calculate field over this point or you calculate field over this point, at every point field will remain same, field will not change. So that is the electric field due to a solid sphere and the field inside the cavity. Just note it down. These are topics which are important for your entrances, but these are not given in NCERT.
सर स्मॉल आर कितना है, क्या है
Small r
सर?
is
मतलब कितना है,
separation.
सेंटर से या फिर सरफेस?
Centers. It's always from the center. Written? Can I scroll it?
Yes, sir.
Sir, can you please scroll up, sir? I haven't written.
Okay.
Done, sir. Can I scroll it? Yes, sir.
Okay.
Sir, can you show the graph once? Thank you, sir.
So after field, we will discuss the potential due to this solid sphere. After this, we will discuss potential due to a solid sphere. So if you have a solid sphere, see, a hollow sphere have charge distributed only on the surface. But if you have a solid sphere, then that solid sphere will have charge on the surface as well as inside. Solid sphere have charge on the surface as well as inside. So you have a solid sphere, the radius of the solid sphere is r. The charge over the solid sphere is q. You're supposed to calculate potential to the sphere. So potential due to this sphere, you can calculate at 3 points. You can calculate potential at a point outside the sphere. You can calculate potential at a point on the surface of the sphere. Or you can calculate potential at a point inside the sphere. So these are the 3 points at which one can calculate potential due to the sphere. So if you want to calculate potential outside the sphere, then outside the sphere, it's simply kq by small r. It's just like a point charge. If you want to calculate potential on the surface of the sphere, then on the surface, this is kq by capital R. But if you want to calculate potential inside the sphere, then inside it's q by inside the sphere, it's q by it's 8 pi epsilon naught r cube 3r square minus r square. So this is the expression of potential inside the sphere. Now, if I ask you to calculate potential at the center, see, at the center, your R is equal to 0. You're calculating all separations from the center. So from at center, your R will be 0. If I substitute these values here, I will get potential inside the sphere is q by 8 pi epsilon naught r cube. It's 3r square. Next, you can cancel this r square and this r cube. This r square will cancel, get 3 r. So potential at the center. This is expression of potential at the center of the sphere. So at the center, it's 3 by 2. I can write this 8 as 2 into 4 pi epsilon naught. It's q by 4 pi epsilon naught r. See, what is q by 4 pi epsilon naught r? Q by 4 pi epsilon naught r is the potential at the surface. So you can say that potential at the center is 3 by 2 times the potential on the surface. So at center, potential is almost 1.5 times greater than that of surface. Now, if I ask you to plot V versus R graph, this is R and this is V. If I ask you to plot this graph, then see, at center, potential is 3 by, this is center, R equal to 0. This is surface, R equal to capital R. This is inside, R is less than capital R. This is outside, R is greater than capital R. So this is the point at the center. This is the point at the surface. This is the point inside, and this is the point outside. So inside, potential is 3 by 2 times of the surface. It's 3 by 2 times the potential of surface. This is the potential inside. At the center, on the surface, the value of potential is Vs. From center to surface, potential is decreasing. At center, it's 1.5 times of the surface, and surface is just Vs. And how is it decreasing? See, inside it's proportional to R square. So if it is directly proportional to R square, that means shape of the graph will be a parabola. So this will be the shape of the graph inside. When you go outside, then outside it goes as 1 by R. It goes as 1 by R. So outside the graph will be high. So this is V out, which is inversely proportional. These are the solid spheres. See, all these graphs, all these expressions, if you look at the previous year's questions of JEE and NEET, then you will get these relations, and these graphs are sometimes asked directly. These are direct questions. They will give you 4 graphs and will ask you to pick the correct one for a solid sphere. Not at all. Then we will start current electricity.
So,
Yes.
so in the V center, sir, it is R cube or R square? So in the
R
denominator.
denominator inside or center?
So at center.
Center, it's R cube, then R square and R cube will cancel. We will left with just R.
Okay. So please scroll.
Written?
done.
So that was about the revision, and the next class will continue. So we were doing current electricity in the last class. Huh? We have finished this resistance and resistivity stuff. Okay, just tell me, what is drift velocity, Hishma? Hishma, are you in class?
Yes, sir.
What is drift velocity, bacha?
Sir,
So the velocity with which electrons drift towards the positive end of a conductor
Okay, so when we calculate drift velocity, before application of cell or after, before connecting cell or after connecting cell?
after connecting.
After connecting cell. So that, what was conductivity, Arpit?
sir, it is inverse of resistivity.
Inverse of resistivity. On what factors does resistivity depends?
Sir, it depends upon length and area of cross section.
Resistivity depends upon length and area of cross section.
No, sorry. It depends. Sir, it depends upon nature of material.
It depends upon nature of material. It's independent of length and area of cross section. It depends upon nature of material and temperature only. It does not depend upon length and area of cross section. That's resistivity. Okay, so we did current density also. Yes, Uni, what is current density?
Sir, current per unit area.
Current per unit area. Okay. Just 1 second. Just 1 second. Sorry. Yes, we were doing current density. What was current density? Current density is current per unit area. Okay, we have finished this thing. We have finished like this question. Like if you change the length of a conductor by 2%, then its resistance and resistivity will change by some amount. Next type of question is, if you have a conductor, the area of cross section of the let's say the radius of the conductor is r, radius of the ends is r, the length of the conductor is L, and I ask you to calculate resistance between these 2 points. Let's call this as point 1 and point 2. I ask you to calculate resistance between point 1 and 2. Resistance between points 1 and 2. You need resistance between point 1 and point 2. The resistivity of the conductor is rho. What is the expression of resistance in terms of resistivity? Maharaj? Expression of resistance in terms of resistivity, Maharaj.
Sir, R equals to rho L by.
R is equal to rho L by. So resistivity is rho, length of the conductor is L, and the area of cross section, the radius of an end is R. So the area of cross section is pi R square. So this is the resistance, rho L by pi R square. That's the resistance of the conductor. It's the resistance between point 1 and 2. You can have other type of questions also. Like instead of this cylinder, you can ask, we can give you a cuboid, a conductor of this shape. Let's say this conductor is given. One side is L, another side is B, another side is, let's say this is B, and let's call this as H. Resistivity is rho. I asked you to calculate resistance between point 1 and 2. So for resistance, you can use this expression R12 is rho. It's L12 divided by area, which is A12. So L12 means the separation between N1 and N2. When the expression of resistance, we use length. That length means the separation between the two ends. So here L12 is L. And A12 means the area of the ends, the area of this end. How much is the area of this end, Miraj? Miraj is not in class. Yes, Noah. What is the area of this particular end, this particular section?
So BH.
BH. One side is B, another is H, so area is BH. So A12 is BH. So you can say that resistance is rho L over BH. This is the resistance, rho L by BH. If I ask you, I take two more points, like point number 3 and point number 4. I ask you to calculate resistance between 3 and 4. It's rho L34 by A34. How much is L34, Ishma?
H.
L34 is H. How much is A34? Area of this particular section, Ishma?
L into B.
L into B. So it's A is LB. It's rho H by LB. So R34. So if you have two ends, he asks you to calculate resistance between two ends. Then just take the resistivity rho. Length means the separation between the two ends, and A is the area of cross section of that end. We don't take area of the entire conductor. We take area of cross section only, area of the end. Okay, instead of 3, 4, if I give you two more points, like a point in the front 5 and a point in the back 6. I ask you to calculate between 5 and 6. It's rho. See, L will be the separation between front and the back face. The separation between the front and the back face is B. Then it's area. Area is the area of the front or the area of the back end. So one is L, another is H. So area is L into H. So this is R56 rho B by H. So this is another type of question on resistance and resistivity, where you have a conductor will be given, length and area of cross sections are known. Note it down. Is it clear? Unib, Arpit, Anshika?
Yes, sir.
Okay, note it down. Okay, the next type of questions will be based on drift velocity, relation between current and drift velocity, current density, that mobility. It will include all the next type of questions. So the next numerical is see the next question is a current of 1 ampere flows through a copper wire of length 0.1 meter and cross section 10 raised power minus 6 meters square. First part. Is specific resistance of copper is 1.7 into 10 raised to the power minus 8 ohm meter. Calculate first part. Potential difference across the ends. Potential difference across the ends. Second part. Current density in the wire. We're supposed to calculate current density. Third part. If there is one free electron per atom in copper, then calculate drift velocity. Drift velocity. So here the density of copper is given, which is 8.9 into 10 raised to the power 3 kg per meter cube. The atomic weight, molar weight of the copper is 63.5 and number of atoms are 6.02 into 10 raised power 3 per kg atom. Do it. No. Written? Ishma, Arpit, Anshika,
Yes, sir.
yes or no?
No, sir.
Tell me once you have written, then we'll start the solution.
Written, everyone? See, current is given 1 ampere. Length of the wire is given 0.1 meter. Area of cross section is given 10 raised to minus 6 meter. What is this? This is resistivity. You're supposed to calculate potential difference across the ends of the conductor. So, Apit, what's the formula for calculating potential difference? Arpit, what's the formula for calculating potential difference? Voltage. Hishma, how we calculate voltage? Noha, formula for calculating voltage?
KQ by R.
No, not K.
Current is given, then how we calculate voltage, Yashika?
Sir, V is equal to IR.
V is equal to IR. See, in this question, I is given 1 ampere, but instead of R, resistivity is given. Noah, can you calculate resistance from this data? Like resistivity is given, area is given, length is given. Can you somehow calculate resistance by combining all these data?
So rho L by.
Rho L by. So you can use, this is I. Resistance you can write, it's rho L by A. So how much is I? Your I is 1 ampere. Resistivity is 1.7 into 10 raised to minus 8. Length of the conductor is 0.1 meter. Divided by area. The area of cross section is this 10 raised to minus 6. So the expression is, it's 1.7 into 10 raised power. See, this is minus 8 and minus 6 will go to numerator. This will be minus 2 and this is 0.1. Good evening, Ashray. So it's minus 2 and minus 1 will be minus 3 volt. Akshay, we are currently doing current electricity. So you just have to wait for 5 more minutes. Then we'll start something fresh.
Okay.
Current electricity basically have 2 parts. So one part is finished. We are just finishing the numericals. In the 5-10 minutes, we'll start the second part. Then I will provide you with the backup of the first portion. So this is how we call voltage. Second part. After voltage, I expect you to calculate current density. Hishma, how to calculate current density, J? Hishma,
Sir,
you're not.
I by A.
Yes. I by A. So your current is I. Area is 10 raised to the power minus 6. So it comes out to be 10 raised to the power 6. What is the unit of current density, Hishma? Hishma, you're not in class, huh?
Yes, sir.
You are in class, okay. What's the unit? Unit, current density unit.
Ampere meter raised to minus.
4 meters square. Third part, if there can be free electrons per atom in copper, then calculate drift velocity. See, for formula for calculating drift velocity is, you can calculate drift velocity from this expression also. I is NEAVD. So from here, you can write that your VD is, it's I by NEA. So Yashika, which value is missing? Like out of these I, NEA, which value is missing? Which is not given in the question.
Sir, N.
N is not given. So to calculate N, he have given you this data. Like free electrons per atom in copper, then calculate drift velocity if there is one free electron. Means if you have one copper atom, that means you have one free electron. If you have 1,000 copper atoms, that means you have 1,000 free electrons. If you have 1 lakh copper atoms, that means you have 1 lakh free electrons. So the number of free electrons is equal to the number of copper atoms. Now, you're supposed to calculate the number of copper atoms in 1 meter cube of copper. This is again the mole concept. But just to help you, he have given you this thing, that n is 6.0202 into 10 raised power. You won't use the data. We need number of copper atoms in 1 meter cube of copper. So volume of copper is 1 meter cube. This is what small n is. Now, what is small n? Small n is number of electrons per unit volume. Number of electrons per unit volume is small n. So per unit volume means volume is 1 meter cube. Volume is 1 meter cube. Density of copper is given, which is 8.9 into 10 raised power 3 kg per meter cube. If volume and density are given, Ishma, how to calculate mass? Uni, volume and density are given. How will you calculate mass?
Sir, density is mass upon volume.
Density is mass upon volume. The mass will be density multiplied by volume. So it's 8.9 into 10 raised to the power 3 into 1, which is 8.9 into 10 raised to the power 3 kg. This is the mass. This is the mass of copper. You're supposed to calculate number of copper atoms in this much of mass of copper. How to calculate number of atoms if mass of any element is given? Noah?
Given mass.
Okay. Then? Okay, let Noah answer. Noah, the mass is given. How do you calculate the number of number of atoms? Yoshika, mass of copper is given. How will you calculate the number of atoms of copper?
Sir, given mass by molar mass into the atomicity.
The atomicity at Avogadro number. So the number of copper atoms is mass of copper divided by the molar mass multiplied by the Avogadro number. So what is the mass of copper? This is the mass of copper. It's 8.9 into 10 raised power 3. How much is the molar mass? The molar mass is 63.5. Multiplied by Avogadro number. How much is the Avogadro number? 6.023 into 10 raised power 23. But the problem is when you calculate moles, Arpit, then you keep mass in kilogram or you convert mass into gram?
So grams and grams.
Grams. Yeah. So this is 10 raised power 3 kg. When you convert it in grams, it comes out to be 10 raised power 6. So to calculate number of moles, your mass should be in gram. It's not in gram, then convert it in gram. So we can let's take some approximations. I'm taking few approximations just to simplify the calculations. I'm rounding off this 8.9 to 9. So it's 9 into 10 raised power 6. Then I will round it off this 6.023 into 6. I'm doing this just to simplify the calculation. This 63.5, I can write this as 6. I'm writing this as 60 almost. 6 will cancel this 10. So this is almost 9 into. See, this is a good method to get the order of magnitude. So 23 or 6, it's 29, 27. So this much of copper atoms per meter cube we have. So if this is the number of copper atoms, Noha, then what's the number of electrons? Number of electrons, what will be the number of electrons? Noha.
Sir, 28 होगा.
Why?
Sir, 9 into 10 to the power 20.
23 or 629. Oh yes, 28. Doha, number of free electrons per unit volume. Each atom contribute 1 electron. So the number of free electron will be equal to number of atom. So the number of free electron will be simply 9 into 10 raised to the power 28 atom per meter cube. This is small n. So once you have a small n, so all these calculations to calculate this is small n. Now you have everything. You have current, you have E, you have small n, you have A. You can calculate drift velocity. How much is current, Arpit? What's the value of current given? Arpit. Ishma. What's the value of current? Arpit, you again have to open your video. Huh? So the current is this 1 ampere. So VD is I, which is 1 ampere. Divided by N number density, which is 9 into 10 raised power 28. Multiplied by this thing, electronic charge, which is 1.6 into 10 raised to the power minus 19. Then you have a area of cross section, which is given like this is area of cross section, 10 raised power minus 6. So this is the drift velocity of electrons in the conductor. Is it clear, Unib, Yashika?
Yes, sir.
Yes, sir.
Next, we'll do temperature dependence of resistance and resistivity. Ishma, is there any issue with your network?
Yes, sir, sometimes.
Okay. Is it clear, this numerical?
Yes, sir.
The last part is clear, or you have doubts while the way we were calculating number of electrons per unit volume? Is that
No.
portion clear?
Yes.
See, in these questions now of the first theoretical part, current density and current, the only tough part is small n, number density of electrons, nothing else. Otherwise, everything else is straightforward. Only the number density is an issue. Apit, all clear?
Yes, sir.
Apit, it's always better if you switch on your video. Huh? See, it's always better if you people switch on your video. I use focus mode so you can't see each other, but at least I can see you. If you have that problem with the concentration, that problem gets solved if you switch on your video. When you know that someone is continuously monitoring you. So Akshay, how was your exam?
Good, sir.
It was good.
Yes, sir.
Did you get any question from the topic that we discussed on that day?
Like the problems were related.
Okay, problems were related. So you got the marks? Not yet.
No, no, sir.
Sure. Okay. So from when your vacations will start?
So it started yesterday.
Yesterday.
Yes. Like
Okay.
today is the official day of vacation.
Okay, and it will last on August, I guess, huh?
No, September, sir.
September, first week.
Yes, sir.
So are you coming back to India during vacations or no? Stay there.
On July 9th, maybe like we'll go to India.
What happened, Saifullah? Very late?
I went to hospital, sir.
Oh, okay, everything fine?
Yes, sir.
Okay, Saifullah, we're just finishing the topic that we have started the last class. We're just doing numericals on this topic, nothing else.
Yes, sir.
So we did numericals on drift velocity, current, resistivity, those stuff. Is it clear? Written, everyone? Noah, Uneeb, noted. तुम लोग ऐसे इग्नोर मारते हो ना कभी कभी नोआ
Yes.
हाँ ऑफलाइन क्लासरूम है ना तो मैं सुनाऊंगा ढंग से okay and Noah if you don't respond in a few days you have to switch on your video just like Akshat Arpit okay so after this the next topic is temperature dependence of resistance and resistivity like how resistance and resistivity depends upon temperature like if you increase temperature then resistance will increase or it will decrease resistivity will increase or decrease that's the next topic temperature dependence temperature dependence of resistance and resistivity and resistivity. So the expression of resistance is this, it's ml by an e squared tau. And this is the expression of resistivity, which is m by n e squared tau. It's m by n e squared tau. So the difference between the expression of resistance and resistivity is just length and area of cross section. So the temperature range for which we are discussing is in that temperature range, length and area will not change. So we'll consider only that temperature range in which length and area will not change. Or you can say there is no significant change in length and area of cross section. So for the temperature range involved, the temperature range involved, no significant change, no significant change in length and area of cross section. So for the given temperature range, the length and area of cross section will not change. So if length and area will not change, so will there be any difference between resistance and resistivity or it will be the same term? Arpit, after this statement, the variation in resistance and resistivity will be same or different? Hmm. See, the resistance, difference of resistance and resistivity is length and area of cross section. If length and area of cross section is not changing, then resistance and resistivity will have same type of variation, right?
Yes, sir.
If you remove these two variations, these two things, then resistance and resistivity are the same thing. So after this statement, you can say that variation in resistance and resistivity will be same. Resistance and resistivity would be same. So for the temperature range involved, there is no significant change in resistance and resistivity. Both will have same variation. Let's first discuss conductor. I'm writing the expression of resistance. It's ml by an e squared. Let's see how the resistance of a conductor varies when you increase temperature. We'll look at each and every term. I'm increasing the temperature. On increasing temperature, does mass of electron will change? Saifullah? If I
No.
increase the temperature, so it will not change. This will not change. Length? No, we have
No.
no. We are taking only that temperature range where length will not change. What about area?
Also no.
It will not change. E, electronic charge? No.
No.
So there will be only N and tau. So when you increase temperature, then number density will not change. It will remain constant. Because see, conductors have trillions of free electrons. When you increase temperature, then some bonds may break. Due to those bonds, some free electrons will get some new free electrons will get released. But that number is very small. As compared to the initial number of electrons, the number of electrons that will release due sorry, internet issues. Am I audible? Voice is clear? It's cracking.
Sir, it's some delay. There is some delay in the voice.
Abid, Ishma,
Sir, it's still lagging.
yeah, is it better, Arpit?
Yes, sir, it's good.
So when I increase temperature in a conductor, the number of free electrons will not change. Number of free electrons will remain almost constant. The reason is conductors have a lot of free electrons, like they have trillions of free electrons. When you change temperature, then some new electrons may release, but they won't have any significant change. It's like say you have in conductor, you have 10 raised to the power 28 free electrons. This is the order of free electrons in a conductor. Due to increasing temperature, some bonds break. Due to breaking of bonds, some electrons get released. Let's say this 1000 electrons releases due to bond breaking. Now, as compared to the initial number of electrons, this change is insignificant. That's why we say that number of electrons will remain constant on increasing temperature in a conductor. But if I increase temperature, then this what happened with the relaxation time? We have discussed while we were discussing drift velocity. Saifullah, what happened when we increase temperature? What happened with the relaxation time? It remains constant in increase, it decrease. What happens with the relaxation time?
It decreases, sir.
Very good. It decreases. So if it decreases and this one is in the denominator, then what will happen with the resistance?
It will
It should
increase.
increase, right? So there's only one term which is changing, and that is relaxation time. So in a conductor, when you increase temperature, then your resistance increases. So if I plot, so in conductor, on increasing temperature, resistance increases. So when you increase temperature, then resistance increases. So this is temperature in Kelvin. This is resistance in ohm. So when you increase temperature, then resistance will increase. This will be the shape of the graph. This is how the resistance will increase. If instead of resistance, he asks
Sir, you are inaudible again.
oh, sorry, so it will not happen again. This just give me 1 second. They Hishma, you are the host now. Can you make me host, Learnivio?
Yes, sir.
Just right click on the Learnivio and there will be option. Yes, thank you. Yeah. So I was asking, what is an alloy? Yashika, what is an alloy?
Sir, it is a combination of more than two or two metals.
Alloy is, yes, right. Alloy is combination of metals. Alloy is the combination of metals. When you combine two or more metals, then we get alloy. So usually the examples of alloys are that we use in electrical equipments is nichrome. Nichrome is the one that we use in heaters. In heaters, we use nichrome.
Sir,
In bulb, we, yes.
So copper is a alloy.
No, no, no. Copper is a metal. It's an element. Metal. Then we use manganese. So when we make an alloy, we have certain criteria in mind. Like when we mix metals to form an alloy, our target is to have minimum variation with temperature. We make alloy, we combine metals in alloy so that the resistance have a very small variation with respect to temperature. So alloys are combination of metals. All metals are conductors. So just like conductors, an alloy also, when you increase temperature, resistance will increase. An alloy also, resistance increase with temperature. But as compared to conductors, conductor variation is small. Conductor variation is small. So if I plot yours, this temperature versus resistance graph, then for alloy, it will be like this. See, it's increasing, but the slope is very less. The increment is very small. So as compared to conductors, the variation is small. So this is how we make an alloy. When you take some metals to make nichrome, then you try to maintain the small variation of resistance with temperature. You need that variation should be small. After alloy, the next is semiconductors and insulators. What's the difference between conductors and insulators?
So insulator does not allow electricity to conduct.
So what's the difference in the structure, Unib? Unib, what's the difference between the structure of insulator and conductor? Maybe in terms of free electrons.
Electron with the insulator.
Insulators have no or very negligible number of free electrons. Same is the case with semiconductors. Semiconductors have very few free electrons. As compared to a conductor, the semiconductors and insulators have very few free electrons. So let's write this expression again. R is ml over A n E square tau. So when I increase temperature or increasing temperature, see, mass will not change, length will not change, area will not change, this will not change. But now the number density will increase because in semiconductors, you have very few free electrons. When you increase temperature, then some bonds may break. Due to breaking of bond, some electrons releases. So your N increases. On increasing N, your R will decrease. And when you increase temperature, just like the previous case, the relaxation time will decrease and R will increase. So see, both parameters are giving opposite effect. Number density is trying to decrease resistance while relaxation time is trying to increase resistance. So overall effect will depends upon the factor which is strong. So this is the strong factor. So no, sorry, not this one. Sorry. This factor is the strong. Alloy and increase temperature, then the resistance will decrease. So on increasing temperature, this is the stronger one. Temperature decreases. So unlike a resistor, a conductor, in semiconductors, insulators, if you increase temperature, then resistance decreases. So this is temperature in Kelvin. And this is resistance, or you can say that this is resistivity. So this will be the nature of the graph. Resistance decreases on increasing temperature. Instead of resistance, if I ask you to plot conductivity versus temperature graph, what will be the shape of the graph? If I ask you to plot conductivity, conductivity is sigma. If I ask you to plot sigma, then what will be the nature of the graph, Yashika? See, resistivity is decreasing. What will happen with the conductivity?
Sir, it will increase.
It will increase. See, conductivity is 1 by resistivity, right? C is 1 by rho. So if your resistivity is decreasing, then obviously your conductivity will increase. This will be the graph. your conductivity will increase. So this is the qualitative discussion on variation of resistance with temperature. Like when you increase temperature of a conductor, then resistance will increase. If you take a alloy, then resistance will increase, but the variation is small. But if you take a semiconductor or an insulator, then resistance will decrease. Next is, if I give you a superconductor, do you know what are superconductors? Does anyone know what are superconductors? No? Okay. Superconductors these are new materials. Superconductors are materials which have zero resistance at a non-zero temperature. Which have zero resistance at a non-zero temperature. At a temperature known as critical temperature. Known as critical temperature. So if I take temperature in Kelvin, and this is the resistivity or the resistance. So in some semiconductors, what happens is when you decrease temperature, then resistance decreases. And at a critical temperature, your resistance will drop to zero. We call this temperature as the critical temperature. This is the critical temperature. This is very, very interesting materials. Because see, zero resistance means no wastage of power. So if you take a loop of copper, you connect this loop to a cell, some current will start flowing through this copper loop, and then you remove the battery. What will happen? This current will continue to move throughout the copper wire. After some time, the current will be zero. Yes, what do you think?
After
I
some
take a
time, be
copper.
zero.
Current will be zero. So where current is zero, that means electrical energy will be zero. Where that electrical energy goes? Listen again. You take a loop, a circular loop. You connect this loop with a cell. Then you remove the cell. Some current is flowing through the wire. After some time, this current will reduce to zero. So current will reduce to zero. That means where this electrical energy goes, this electrical energy gets wasted in the form of heat due to resistance. Now assume if this wire have exactly zero resistance, I connected the cell, then I remove the cell. Then what will happen? Current will, at any time, current will reduce to zero. It will always flow in the coil.
It will be the same.
It will be the same. So always the same current will keep on flowing through the coil. So if you are using a coil or something which is made of superconductors, then the wastage of energy will be minimal. See, if you say, if a fan is running through some battery or cell or something, then the major part of the energy gets wasted in the form of heat due to resistance. You take any electrical appliance, you take a fan or a bulb or anything. When you switch on that device, that after some times it becomes hot, right?
Yes, sir.
Answers.
Sir, can you repeat? You got stuck.
Yes. Am I audible now?
Yes.
It's okay. I'm asking, like, if I take a fan, I switched on the fan. Yes, a normal ceiling fan. When you switch on the fan, after some times the fan gets heated up, right? It becomes hot. So I'm asking from where that heat energy is coming.
From electricity flowing through it.
Means your electrical energy is getting converted into heat energy. So why are you supplying that heat energy? Are you supplying the heat energy? Sorry, that electrical energy You're supplying electrical energy to the fan to rotate or to heat up?
To rotate.
To rotate. So the energy, the electrical energy that is getting converted into heat energy is the wastage. So when you switched on the fan, a major amount of your electrical energy gets wasted in the form of heat. It's due to resistance. But assume if you have a fan made of some superconducting material, then that means there is no wastage of energy. The power, the power wastage will reduce exactly to zero. So it's like you take a fan, you connect that a fan which is made up of some superconducting material. You connect that fan with a switch. You switch it on. When the current starts flowing through the fan, you can switch it off. Then it will always keep on rotating because there is no wastage of energy if you have superconducting materials. We have superconducting materials. The problem with the superconductor is the transition temperature is very small. Like the temperature at which a material becomes superconductor is very, very small. It's around some 200 degrees Celsius, minus 200 degrees Celsius. This is known as liquid nitrogen temperature. At this temperature, there are few materials which behaves like a superconductor. We use superconductors in MRI scans and all things. They use superconducting materials. Have you heard about bullet trains?
Yes.
The bullet trains have these superconducting materials in the bottom. The speed of the bullet trains is due to superconducting materials. If there is no superconducting materials, then bullet trains can't run at that speed. So that is superconductor, which can have exactly zero resistance at some non-zero temperature. That temperature is known as critical temperature. So this discussion was qualitative. The next is quantitative. Like if you change temperature, then how resistance will change. Like the numerical value, the relations through which you can calculate numerical value. We call this as quantitative discussion. Quantitative relation. So the relation between resistance at different temperature is this R naught 1 plus alpha T minus T naught. The derivation of this expression is not a part of your syllabus. We will not derive it. You just have to remember the relation and then we'll do numericals on it. Look each and every term. R naught is resistance at some temperature T naught. Resistance at temperature T naught. Okay, Akshay. So R naught is resistance at temperature T naught. RT is the resistance at temperature T. This T is usually greater than T naught. So you can say that this RT will be greater than R naught. So the temperature T is greater than T naught. So RT will be greater than R naught. And this alpha is the temperature coefficient of resistance. Means for different material, the value of alpha will be different. Different materials will have different values of resistance for the same temperature variation. Like if I take copper and if I take, let's say gold, at 10 degrees Celsius, their resistance is, let's say 10 ohm, and this is also 10 ohm. At 30 degrees Celsius, like I change the temperature by 20 degrees Celsius for both. For copper, the resistance is 12 ohm. For gold, the temp resistance is, let's say 15 ohm. So that means this variation in resistance along with temperature also depends upon the nature of material. The dependency of the nature of material is given by this alpha. So this is alpha, which we'll call temperature coefficient of resistance. Its SI unit is SI unit of alpha is, it's either Kelvin inverse or its degree Celsius inverse. You can use both the units. The SI unit is Kelvin inverse, but you can also use degree Celsius inverse. Remember a few more things, like For conductors, if you take a conductor, alpha is positive because in conductors on increasing temperature, resistance increases. Alpha is positive and it have a large value. For alloy, alpha is positive but extremely small, very, very small value. For semiconductors and insulators, Arpit, what happens when we increase the temperature of semiconductor or insulator? Kishma, what happens when we increase the temperature of a semiconductor or insulator? Noha, if I increase the temperature of semiconductor, what happens with the resistance? Yes, Noha. What happened with the resistance if I increase the temperature? Resistance
It increases.
decreases. So alpha is negative. So we'll do numericals on this concept. This T naught is sometimes known as reference temperature. T naught is reference temperature. Its value is either 0 Kelvin, or sorry, not 0 Kelvin, 0 degree Celsius or room temperature. So if it is not given, then we will take T naught as 0 degree Celsius, or you can take it as room temperature. That's the reference temperature. It's either 0 degree Celsius or it's room temperature. Note it down. Then we'll do some numericals on it. Is there any doubt in this whole discussion? Arpit, Ishma, Saifullah, Yashika.
No, sir.
Okay, just note it down. Then we'll do numericals on this concept. Note it down.
Can I scroll it? Noted. Can I scroll it further? Saifullah, written?
Yes, sir.
No, I need 3 more lectures, at least 3 more lectures to finish.
Sir, open. Yes, sir.
Doubts, discussions? Yes, written everyone? Okay, so we'll stop here. In the next class, we'll continue with circuits. We'll do 1-2 numericals on this topic, and then we will continue with circuit series and parallel combination. The second part of current electricity. Okay, let's stop here. Bye.